today doing heterogeneous equilibria, where we talked about and reviewed that only solids and liquids are not included in the KEQ and in the KP. And the reason is that only gases and aqueous change concentration. So therefore, we just plain don't include the PCl3 and the PCl5 in the KEQ. So for this equation, for example, a KEQ would only include the concentration of the chlorine gas, and the pressure would only include the pressure of the chlorine gas. And now we're talking about heterogeneous equilibrium and change at equilibrium, and this is going to include something called an ice table. And an ice table is a huge concept, which I didn't mention. It's a huge concept. It's prevalent in many, many different situations, including acids and bases, titrations, and all kinds of things. So this is gigantic. So here's an example problem. Carbon monoxide and hydrogen create methanol. At 780 degrees Celsius, initially our concentrations are as follows. Our carbon monoxide concentration is 0.500 molarity. And our hydrogen concentration is equal to 1.00 molarity. At equilibrium, and eventually you get to abbreviate all of this, but for right now, let's just lay it all out so that we know what we're talking about. Our carbon monoxide concentration is equal to 0.15 molarity. The question is, what is the value of the KEQ at equilibrium? So first, before we get involved in this, let's lay out what the KEQ is, all right, so that we're sure of what the formula is that we're actually looking for. So this is the problem, and let's lay out. So we know our KEQ is going to be equal to the concentration of the methanol at equilibrium divided by the concentration of the carbon monoxide multiplied by the concentration of the hydrogen squared. And this is all going to be at equilibrium. So we want to know, what are these concentrations when the reaction has hit equilibrium? Does that make sense? So we start the reaction out with these two concentrations here and here. We put them into the container, and then we wait. And when the concentration has reached equilibrium, when the reaction has reached equilibrium, what we know is that the carbon monoxide is at this molarity. But we don't really know anything else. And what we want to know is, what's our K at that temperature, and what is the KEQ? So we have this process that we use that is very helpful, called an ice table. And an ice table looks as follows. We write down initial, change, and equilibrium. And that's where the ice comes from, ICE. And then across the top, we're going to write all of the parts of the equation. So we have the carbon monoxide, we have the hydrogen, and then we have the product, which in this case is the methanol. And now what we're going to do is we're going to write down the concentrations that we know. So what we know is our initial carbon monoxide is 0.500 molar. And our initial hydrogen is 1.00 molar. And we also know that our initial methanol is 0. We know this because there's nothing there when we start the reaction initially. Now, what we also know is that at the end of this reaction, when it's reached equilibrium, our carbon monoxide is 0.15 molar. That's what we know, right? Now, because of this, what we can figure out is that the change in the carbon monoxide is 0.5 minus 0.15. And so therefore, the carbon monoxide has lost 0.35 molarity. So going into equilibrium, the carbon monoxide molarity went from 0.500 moles per liter to 0.15 moles per liter, and so the change is 0.35 moles per liter. Now, when I look at the equation, for every 1 mole that travels across to methanol, 2 moles of hydrogen travel across to methanol. And so therefore, what I do know is that the change of hydrogen going across to methanol is going to be minus 0.70 molarity. Does that make sense? Twice as much. Which means that the amount of hydrogen left is 0.30. Now, what I also know is that for every 1 mole of carbon monoxide going over, 1 mole is produced. So I also know that plus 0.35 is produced. So 0.35 is produced. Questions? Louis, do you have a question? No, okay. All right. Okay, so now I'm ready to plug in because I know that at equilibrium I have my concentrations now, all right? So I'm ready to plug in for my KEQ. My KEQ here is going to be my concentration at equilibrium of my methanol, 0.35. And that is going to be divided by my concentration at equilibrium of my carbon monoxide, which is 0.15. I can. Times at equilibrium my concentration of my hydrogen squared, 0.30 squared. Now, when I multiply all this out, what I get is 26. So that is the ratio. Remember, this is a ratio. That's my KEQ at equilibrium. So are products favored in this reaction at equilibrium? Yes, products are favored. Okay? Questions? Okay, let's try another one. You ready? So this ICE table here, this allows you to plug in all the information you know. And we're going to do ones where there's like missing information and you have to use X. And there are ones where you have to use the quadratic formula. Now, you will never have to use the quadratic formula on the test itself because they can't guarantee that you're holding one of your calculators and not one of my calculators. And I can't do the quadratic formula, like plug it in. You guys get to plug it in and then press enter. I don't get to do that. And it takes me too long to do it. So you're not going to have to do it. But you are going to have to do ICE tables, but they'll all work out pretty. So we'll talk about that, all right? All right, here we go. But you have to set up ice tables, and then they say things like, in the ice table, what is the change? What does X represent? That's how they handle it. They like have you fill in the blanks in the ice table. Okay, here's your next problem. I like them. I think they're fun. Okay, consider this equation. So this is example 2. Here's your equation. 2-methane gas yields, decomposes to produce ethine gas plus 3 hydrogens. The temperature is 1700 degrees degrees Celsius. Initially, your methane concentration equals 0.115 molarity. And your equilibrium concentration of your ethine is equal to 0.035 molarity. Find your KEQ at equilibrium. Okay, do you want to try it? And then we'll get back together, all right? Any kind of concentration, all right? Because you can track the adjustments of any kind of concentration that you're following, whether it's hydrogens and hydroxides for acids and bases, or any kind during titrations, or just concentrations or pressures or anything, all right? Okay, so that's what we've got for today, and then tomorrow we're going to do Le Chatelier's principle, and then we're going to start moving into more complicated ices, and how stresses on the system cause the shift in the ice tables. All right.